When high-sulfur iron drops below freezing, it loses its ability to flex. Under the immense pressure of the North Atlantic, this 1-inch fastener simply shatters. The Titanic was constructed using 3 million of these rivets, each one a critical link in the structural integrity of the hull. Historically, we have attributed the sinking to a single unavoidable event, a massive iceberg collision that sliced through an otherwise perfect ship. However, forensic analysis of the steel and the original construction logs suggests the ship's physical reality was already diverging from its reputation for perfection. To understand why it went down, we have to look past the tragedy and perform a strict engineering autopsy on the hidden logic of its design. Deep within the lower decks, stokers worked in a high-pressure environment, feeding a massive industrial system that required constant fuel to maintain its speed. In the days leading up to the collision, a massive coal fire was burning in Boiler Room 6, reaching temperatures close to 1,000 degrees Celsius. Heat at that intensity, applied directly to the hull for 10 days, bakes the steel plates. This changes the molecular structure of the metal, making it brittle and permanently reducing its thickness. This damage was known, but the pressure to meet the maiden voyage's arrival schedule meant the fire was treated as a manageable inconvenience rather than a structural threat. When the iceberg finally struck, it hit the specific section of the hull that had already been weakened by intense thermal stress. Building a hull on this scale required fastening thousands of steel plates with millions of rivets, a process that varied by location. Because hydraulic machinery couldn't reach the curved sections of the bow, those plates were secured by hand-hammered iron rivets. These specific fasteners contained high levels of sulfur, a chemical impurity common in the early 1900s. This comparison shows how high-sulfur iron reacts to stress. While standard steel bends, this chemical composition undergoes brittle fracture in freezing water, shattering under load. As the iceberg applied pressure, it sheared the heads off these frozen rivets, unzipping the seams. The impact simply triggered a release of energy that the low-quality iron seams were chemically incapable of absorbing. Even with the hull breached, the Titanic was designed to survive thanks to 16 watertight compartments. This schematic reveals a fatal oversight. To allow for spacious upper decks, the watertight walls stopped 15 feet above the waterline, left completely open. As the bow filled, pulling the ship down, water reached the ceiling and spilled over, creating an unstoppable cascade. The designers calculated for horizontal flooding, but hadn't accounted for a multi-compartment breach that would pull the entire system below the surface of the ocean. The fire-damaged hull, the brittle iron rivets, and the open-topped bulkheads aligned to create a situation where survival was physically impossible. Today, the wreck sits on the seafloor as a quiet record of these engineering failures. These photographs of the men who built her show a deep sense of perceived dominance over the ocean. At the time, their manufacturing was considered the peak of human achievement, but the forensic evidence shows that the sinking wasn't a random accident. It was the predictable result of materials and designs pushed beyond their limits. The Titanic remains a monument to what happens when industrial pride leads us to believe we have calculated away the risks of